We're doing a deep dive today into a really foundational piece of science history, Ernest O. Lawrence's Nobel lecture from 1951.
Right. And our mission really is to find that one key insight, that pivot point where nuclear research just completely changed course.
And it all starts around 1928. The big goal was to crack open the atomic nucleus. To do that, you needed to accelerate particles to millions of electron volts.
MIV, right.
Exactly. That was the next great frontier. But the how was a huge problem.
I was surprised reading this because they pretty much dismiss big ideas right away, like Van de Graaff generators or even giant Tesla coils.
They did. And it wasn't just a technical problem. It was, a money problem.
A huge financial one.
A massive one. You needed these enormous voltages, which meant you needed vacuum tubes that were meters and meters long. Most labs they couldn't build them.
They didn't have the space or the budget.
Precisely. The real limit wasn't the voltage itself, it was the wallet.
Okay, so that sets the stage for the big moment. It's early 1929, and Lawrence is reading an article. By an engineer named Waderow. And it describes this clever idea of multiple acceleration, using an oscillating voltage to give a particle a series of small kicks.
A linear accelerator. But Lawrence saw the flaw immediately.
He did the math. And, to get to the energies he wanted, the tube would still be awkwardly long. We're talking several meters.
Just not practical for a lab bench.
Not at all. So his genius was to ask, why go in a straight line for meters when you can just go in a circle?
Bend the path, the ultimate space saver.
He imagined taking just two electrodes, these D-shaped things that he called Ds, and using a magnetic field to curve the particle's path back around again and again.
And this is where we get to the core insight, isn't it? The cyclotron frequency.
This is the magic. He figured out that in that magnetic field, the time it takes for an ion to complete a circle, its angular velocity, is constant. It doesn't matter how fast the particle is actually going.
Wait, hang on. So the particle is gaining energy, it's moving faster and faster, but each lap takes the same amount of time.
Exactly, because as it speeds up, the magnetic field pushes it into a wider and wider circle. The distance increases perfectly to match the speed, so the timing is always the same.
So it's like a built-in clock keeping it perfectly in sync with the electrical kicks.
You got it. That's the secret sauce. A machine that fits on a table could now do the work of one that was meters long.
What I love, though, is how he makes a point to credit Professor G. Ising from 1924 as the real originator of the multiple acceleration idea.
It really speaks to his integrity. And things move so fast. By 1930, his student, M. Stanley Livingston, had a working model.
And the results were pretty impressive.
Oh, absolutely. It produced 80,000-volt protons, but get this, it only applied less than 1,000 volts to the gaps. That's real leverage.
But that early work also led to one of science's biggest what-ifs, a huge near miss.
It really was. They were confirming things, like the disintegration of lithium, but they were using these Geiger counters that were just going wild. The readings were high and all over the place.
So they thought the equipment was just faulty, unreliable.
They did. They concluded the counters were broken and switched to more stable ion chambers.
And the problem was?
The counters weren't broken at all. They were faithfully recording the signals of new artificially radioactive substances they had just created. They literally threw out a Nobel-winning discovery because they thought their gear was bad.
Wow. That's a painful lesson in trusting your instruments.
It is. But they scaled up. They brought in an engineer, W.M. Brobeck, who Lawrence says introduced sound engineering practice, and that's what led to the bigger machines and eventually the transuranium elements.
But scaling up created a new problem, a universal speed limit.
Right. Relativity. Once you get particles moving close to the speed of light, around 100 MeV, they start getting heavier.
So they get too heavy, they slow down, and they fall out of sync with those perfectly timed kicks.
The whole system breaks down. The solution, which came after the war from Macmillan and Wechsler, was called phase stability. It basically adjusts for that weight gain.
And that gave us the synchrocyclotron.
And eventually, the proton synchrotrons, like the Bevitron, aiming for billions of electron volts. BeV.
But even then, Lawrence saw a more elegant way forward than just building bigger and bigger rings.
He did. He suggested instead of just pushing protons harder, why not accelerate heavier things, like a carbon ion with multiple charges stripped off, C6 plus BeV rake.
A heavier payload.
Exactly. You could accelerate that C6 plus ion in the existing Bevitron and get energies over 36 Bevijon. A huge leap without a new machine.
It's just amazing that this entire field, this whole trajectory, came from one simple realization. The problem wasn't the energy, it was the geometry. a linear problem that could be solved by folding it into a circle.
A complete reimagining of the path.
So that brings us to the final thought for you to take away. What major limitation you might be facing right now isn't actually a resource problem, but a geometry problem? What happens if you just bend the path?